It's called arenes. Arene. Arene is a general name for aromatic compounds like benzene. Like benzene. Sorry, I think the structure is not okay very well. Okay, so and benzene derivatives like toluene. Toluene is a methylbenzene. Okay, so this is a benzene and this is toluene. Now, as you notice here that these guys ends with ene, toluene. So as well, arenes. So since they are aromatic compounds that ends with ene, so that's arenes, benzenes, toluene. So, but we have a derivative called ari. Ari are aromatic compounds. The name of aromatic compounds whenever they are joined to another compound. So it means that whenever aromatic compounds want to join to another compound, their names change from arene to ari. So in this case now, benzene changes from benzene to phenyl. And as well, toluene changes from toluene to benzyl. So benzyl is the name of toluene when it is attached to another compound, you get that, or another atom. So we can conclude that whenever an hydrogen is being removed from a arene compound, we have Ay. What do I mean? This is benzene, C6H6. When I remove an hydrogen from benzene, I have C6H5. So it means this is benzene, and this is phenyl. Benzene attached to another compound is called phenyl. Toluene attached to another compound is called benzyl. Alright, so then there's another thing that we talk about. We have hydroxy group. Sometimes phenyl, whenever we add hydroxide group to benzene, so we have phenol. So and this is the case of it. So this is benzene, right? Now benzene is attached to an alcohol group, which is all group, or. So since alcohol group are ends with or, so therefore we have phenol. Okay, so these are the things that I want to talk about. And again, there is another things I would like to talk about is about alkanes. Alkanes are hydrocarbons. They are saturated hydrocarbons, and whenever they are attached to another compound or to another atoms, their name change from alkane to alkyl. Just like arene change from arene to ari, so alkane change from alkane to alkyl. And example is this. Let's say we have methane, CH4. This is methane. So whenever methane is attached to another compound, so it changes to methyl. So this is methane. Oh, sorry. and this is methyl. Alkane, alkyl. Do you understand now? So these are names of compound change whenever they are attached to another compound. So this is another thing I'll explain. Then before we move on, let me also talk about this thing that's also very, very important. When you say carbon is a primary carbon or a secondary carbon or tertiary carbon, what do we actually mean? Okay, let's consider these guys. Now, let's consider these guys. So let's consider these guys. I'm coming. I'm sorry, let me clean these guys. I think I should make it clearer. Okay, so let's check this compound. Let's consider these guys. Let me do it on my own. Now, we check this compound. That's methyl. Am I right? But if we check next compound, there's an attachment there. Then take this one as well. Alright, so if we check the first compound, see that all the attachments around the carbon, in this case, they are all hydrogens. As you can see, hydrogen, hydrogen, hydrogen. So we call this carbon methyl carbon. Methyl carbon. Because all the hydrogens, all the attachments around it are all hydrogens. Do you get that? Now, check the next carbon, the next compound, rather. So this one, we have an alkyl group. By the way, our alkyl group are represented by R. Do you get that? R. So they can be methyl, they can be ethyl, propyl, butyl, pentyl, etc. Okay, so now an alkyl group is attached to the carbon in this case. So, and it is just only one alkyl group that is attached to the carbon. So therefore, we call this compound and this carbon here, we call it primary carbon. This is the primary carbon. So we call this carbon primary carbon. Then check these guys here. We have two alkyl group attached to the carbon. Am I right? So attached to the carbon directly. So in that case, we call this carbon secondary carbon. Then check the third one. There are three attachments around the carbon directly. So therefore, we call this carbon tertiary carbon. Tertiary carbon. So those are the things that are very important that you have to note. So when they say primary carbon, you know what they mean. Secondary carbon, you know what they mean. And when they say tertiary carbon, you should know what they mean by that. And then another thing is this. You can also say that tertiary carbons, they are substituted carbons. They are more substituted than secondary carbon. What do I mean? The meaning is that their hydrogens have been replaced by an alkyl group. So do you get that? So then secondary carbons, they are less substituted then compared to primary carbons, and then compared to methyl carbons. So in methyl carbons, there is no any substitution, there is no any alkyl group. So secondary primary carbons is less substituted to get that. So because there is still space that elements can attach by displacing the hydrogens. So then secondary carbons is also more substituted than the primary carbons. Then tertiary carbons has no space for any other atom to join. Okay, so therefore, and there's another thing I want to emphasize in this case is that the tertiary carbons, their key group are called steric hindrance. So I think I've talked about it in SM reactions, so that the hindrance around the carbons are called the steric hindrance. They are key group that are surrounding the carbon tertiary carbons are called the steric hindrance. Alright, all these things, they have implications, and as we move on during the course, I will still explain more about them. Alright, now let's start with introductions to ITER. Now, introduction. For introduction, so phenol alcohol, ether, these compounds, they are said to be organic derivative of water. What do I mean? So when I say phenol, that's hydroxybenzene, alcohol, and ether. So they are said to be organic derivative of water. So they all come from water structure. Let's consider this structure here. This compound on the screen is water. Now, when an hydrogen from water molecule, when an hydrogen from water molecule is being replaced by an alkyl group, so we have something like this. So this compound changes to alcohol. Good. And sustain here. Then when the two hydrogens are replaced by an alkyl group, we have a different compound. So as you can see from here, that the two hydrogens are being replaced by an alkyl group, and here we have ether. Good. So, and as well, when the instead of an alkyl group, let's say the hydrogens is being replaced by one of a ring compounds, aromatic compounds like phenol. or like phenyl rather, maybe benzene. You get that? No, when benzene is attached to a compound or to an atom, it is called phenyl or phenyl. So maybe it's phenyl. So I'm using pH to represent phenyl. So and the hydrogen is air. So therefore, this compound gives what they call phenol functional group. Phenol is a functional group itself. Good. So these are the derivative of water, because as you can see that all of them, they come from water structures. And as you have noticed here, as we come down, except for phenol, apart from phenol, from this place to from here to here, as we come down, you see that their reactivity decreases, because the hydrogens are being replaced by an alkyl group. So as they're coming down, the hydrogens are more replaced. So in ether, there is no replaceable hydrogen. So that's why that ether is kind of unreactive. So this is kind of unreactive, and alcohol is reactive. It's more reactive than ether, and water is very kind of a good solvent. So let's talk about the nomenclatures of ether. So this is just basic introduction to ether as a structure of ether. So and now we talk about the namings of ether. How can we name ether? So in this video I will talk about three methods of namings. Three methods. So the first thing is this. Now nomenclature. Okay, so first thing I'll talk about is using ether parentheses. Using ether so now using these parentheses, we can name ether in this format. Let's check example. Let's say we have alright, so this compound A is ether, am I right? Because this is a methyl and this is ethyl. Okay, so to name this compound now, you have to, using these parentheses, you have to follow what we called alphabetical order. So you name like this: alkyl, ether. This is the format: alkyl, ether. So the one with the you are going to follow the alphabetical order. So the one that has how do I put it? I mean the alphabetical order. So you have to put the letter that comes first before the other one. So now in this case, now just check between M and E, which one comes first? So E comes first before M. So therefore you say ethyl, methyl, then you name the middle one. That's oxygen, that's ether. As simple as that. So this is how to name this compound. So you follow functional group, you follow the alphabetical order, then you name alkyl, ether, ethyl methyl ether. So let's check another example. Let's check this example. Let's say we have benzene ring attached to oxygens and have okay. So let's check this compound. So this is phenyl, am I right? And this is ethyl. So between E and M and P, sorry, which one comes first? So E comes first, right? So therefore the name of this compound is ethyl phenyl ether. Alright, so this is how to name compounds like this. Then let me put one more example. Let's check this compound as well. So let's check this compound. So this compound here, I'm coming, let me make it. So let's check this compound. This compound, as you can see, this is phenyl, am I right? And this is what? 1, 2, 3. This propyl. Alright, so we check very well. Two of them start with P. Now we move to the next letter. So between R and H, which one comes first? H, right? So therefore you say this compound is phenyl propyl ether. Alright, so this is how to name ether using ether parentheses or alkyl parentheses. So but there is one thing I want to emphasize in this case. There is a situation whereby we have a symmetrical ether. So symmetrical ether. Then when we have a symmetrical ether, we have to so let's check this guy. Situation like this. Let's say we have CH3 okay. So this is what we call a symmetrical ether, situation whereby the two sides of the oxygens have the same attachments. So and we call it symmetrical ether. So and in this case now, to name this type of ether compound, so know this is methyl, and this is also methyl. So to name this type of symmetrical ether, so you just have to use this formats: di-alkyl ether. So therefore the name of this compound is dimethyl ether. So though some people they don't even try to put the di, they just say methyl ether, since you cannot have ether structure without putting the two methyl there. So now, so dimethyl ether. So this is the name of the compound. Alright, so we can check some other examples as well. So let's try some examples on this. Let's check this compound. Okay, let's check this compound. Okay, so this compound here, so as you can see that this guy here is what? This is benzyl. So this is benzyl. So because there's a carbon here, so this is benzene, and this is also a benzene. So this is another example of symmetrical ether. So, and to name this compound now, how do you name this guy? Say this is dibenzyl or benzyl ether. Good. So these are the name compounds using these parentheses. Okay, so another one I will talk about is using the IUPAC. So these are another examples of naming. So using IUPAC. Now using the IUPAC format, so you need to analyze some things. So here you have to use what we call the alkoxy-alkane format. Now, in this case, now you have to use what we call the alkoxy-alkane format, and in this case, we talk about ether. So we mean R O R. Am I right? So this ether, right? So and by the way, when we write OR or RO anyhow, so it means alkoxy. Alkoxy. So when it has charge, it is called alkoxide. Okay. So now this ether structure. From ether structure, the OR part is said to be the alkoxy. Then this is the alkane. It serves as a parent name in this case, though it is attached, but it is served as a parent name, so that's why it is called alkane. Okay, so therefore the combination of these two names gives the IUPAC names. So we call it alkoxy alkane. So therefore we have a compound like Ca3 CO C2 Ca3. So we have compound like this. Before using this example, let me use this example first. Let's say we have this compound. Now, we have this compound like this, so therefore one of them just be this is the alkoxy. Am I right? So and this alkoxy is what? Since it has only one carbon, that's methoxy. So if it two carbons, that's ethoxy. Okay, so this is methoxy. Then this is what? Methane. Methane. And this compound is methoxy methane. Alright, so now let's check this one. This second example here. This second example is quite different from the first one, because to determine which one to be the alkoxy, the one that will be the alkoxy between these two carbons, between these two, since they are different. So to determine which one to be the alkoxy, so you have to focus on which one has the shorter number of carbon. So the one with the shorter number of carbon, or the one that is less bulky, so it's said to be the alkoxy. And here now, between the methyl and the ethyl, which one do you think will be the alkoxy? So therefore this one will carry the alkoxy part. So therefore we have methoxy ethane. So the shorter one, the one that has shorter number of carbon will carry the alkoxy. So and in this case now we have methoxy methane. So and not this is the correct one, and not ethoxymethane. So this is wrong. You get. So this is how to name ether using the IUPAC naming method. So another one I will talk about is how can we draw ether structures. How can we draw ether structures? So we are given ether names. How can you turn the names to structure? So this is very important as well. So let's say we are given this name now. 3 ethoxy hexane. So 3 ethoxyhexane. So let's say we are given this compound. So how do we convert this compound to structure? So it's very important. So the first thing is this: you check at the parent's name, the last name that is there, hexane. Alright, so once you check at the hexane, so it means that you have to draw hexane out first. So 6 carbons: 1, 2, 3, 4, 5, 6. Now, once you draw the 6 carbon out, so the next thing is to go to the solvents. So they said 3 ethoxy. It means that the meaning of 3 ethoxy is that there's ethoxy on the 3rd carbon. Simple. There's ethoxy on the 3rd carbon. So just count 3rd carbons and put ethoxy there for them. So therefore 1, 2, 3. So that's here. Then put ethoxy for them. So this is ethoxy. So C2H5. Look at that. So no, ethoxy is an alkyl group plus oxygen. So this is ethoxy. So therefore this compound is ethoxyhexane. So because this is the ethoxy part, so this is the ethoxy part, and this is the alkane part. So hexane. So ethoxy, 3 ethoxyhexanes. So this is compound. Okay, so you start with the parents' names. Now let's check another example. Let's say we have 2-methoxypentane. 2-methoxy pentane. So to draw this compound, what do you do? So you start from the parent's name, then so you draw the parents out. That's pentane. That's 5 carbons. 2, 3, 4, 5. Then you go to carbon 2 and put methoxy there for them. So this is carbon 2. Then put methoxy there. C3. So this is 3-methoxypentane. So this is methoxy and this is pentane. Okay, so this is very simple to draw. Then another naming of ether that I'll talk about is using the tribal names, and this is not very common. So example, now we have so methoxybenzene is called the anisole. So for example, or you have furan. So those ones are in your slide. I don't have to go over them because they are not actually very important. So but let me just draw them in case of. So So this is said to be anisole. Then again, we can also have furan, THF, so tetrahydrofuran. So this furan. So THF. So this is said to be furan, tetrahydrofuran. Alright, so this naming copper, naming ether this way, so it's said to be trivial names. So they are not very common names. Alright, so this is all about the nomenclature of ether. So the next thing I will look at and I'll try to discuss is the chemistry of ether. So chemistry of ether. Now, the chemistry of ether has to do with the alkoxy group. So, and as you know that ether is from water structures. So, and all the hydrogens in water structures in ether has been replaced by an alkyl group. So, which make ether less reactive. So, ether is unreactive, unlike alcohol and water. Okay. We have two oxygen groups, ether and alcohol. Now when I say alcohol, we mean alkanol. Okay, so we have two oxygen group, ether and alcohol. So what do I mean? This is ether. Both contain oxygens from water. This is ether and this is alcohol. And this is ether. And this is alcohol. So by comparing their reactivity, ether is the one with the least, or is, can we say ether is less reactive. So because ether did not have a replaceable hydrogens, unlike alcohol, you get that. So ether is less reactive because it doesn't have a replaceable hydrogen. So this is the reason why ether is less reactive. And let's talk about some interesting features of ether. First thing is that ether acts as Bunsen-Lowry base. So ether acts as Bunsen-Lowry base. So it acts as Bunsen-Lowry base. So what is Bunsen-Lowry base? Now, according to Bunsen-Lowry theories of acid base and acid base, so it said that acids are proton donor. So and base, Bunsen-Lowry base. So he said that acids are proton donor and base are proton acceptor. So though ether may be weak Bunsen-Lowry base because it only accepts proton, or it can only be protonated by a hot and concentrated strong acid like hydrogen iodide, or hydrogen halides like hydrogen iodide or hydrogen bromide or hydrogen chloride, a conc and very hot strong acid. So let's recall from this. Let's take some step backward a bit. So I'm explaining this theory. Let's say this is a compound. Now, so All right, so we check this compound now, and this reaction rather. So see that these 4 species now. So this first one has donated an hydrogen to donated the proton to ammonia. Am I right? So HCl donated the proton to ammonia. Therefore, it makes HCl to be benzaldehyde acid. You get that? So it makes HCl to be benzaldehyde acid, and because ammonia accepts proton from HCl, so HCl donated a proton to ammonia, and HCl becomes chloride, because it has donated its hydrogens to ammonia. So, and this is called conjugate base. So because ammonia accepted protons from HCl, so it makes ammonia benzaldehyde base, and ammonia accepted the protons and becomes this guy. So therefore, this is conjugate acid of ammonia. So therefore, we can conclude that benzaldehyde acid-base theory stated that acids are proton donor and base are proton acceptor. So how does this one affect ether? Now, ether also can be protonated by, I said ether is unreactive. So though it is unreactive, but in a very serious condition, like in vigorous conditions or situations, so under a very strong and very concentrated strong acid at high temperature, so ether can react with the strong acid to give conjugate acid together. To give conjugate acid, so it can react with a very strong acid. So, and that reaction leads to cleavage of ether, which we are going to talk about later. So, and let's see how reaction goes this way. So let's say we have an acid, a very strong acid in this case. So this very strong acid now reacting with ether. So let's say this is ether. Good. So the thing is that the acid, as ether acts as a benzaldehyde base. So what happens? So as benzaldehyde acid will donate proton, and benzaldehyde base will accept the protons, and it becomes this. So, and as we can see that these protons from this guy here, so this proton will come to this guy, and the ether become protonated. So become protonated. Sorry, I want to put a lone pair. Let me put a lone pair on this side. So with positive charge. Alright, so similarly, as you can see here, so we can conclude that this is an acid, this is a base, because why? It accepts a proton from the acid. Am I right? So, and this is the conjugate base, and this is conjugate acid. So you see, so, and this conjugate acid is said to be protonated ether. So before ether can undergo any reactions, it has to be protonated first. So this is what we call activation of ether. So it has to be activated, by protons. So we call this protonated ether by a very strong acid. A very strong acid, I said very strong acid, a very strong acid under high temperature. Oh, sorry, under high temperature. So now, then this reaction shows that ether is a Bunsen-Lowry base, though it's a Bunsen-Lowry weak base because not every acid can react with ether, so only strong acid can react with ether. So that makes it a very strong and a very weak Bunsen-Lowry base. So it's a weak Bunsen-Lowry base. So weak base. All right. So also another interesting thing about ether is that ether can also act as Lewis acid. So ether can also act as a Lewis acid. So ether can also act as a Lewis acid. As a Lewis base rather. Sorry. So as a Lewis base. Lewis base rather. So, and why is that is Lewis base? From Lewis acid base theory. So he said that acids are electron pair acceptor and base are electron pair donor. So now, and to be very concerned about this, so we can also conclude that any compound that has lone pair is a Lewis base. So what do I mean? So let's check this guy, ammonia. So ammonia has a lone pair, that's why ammonia is a Lewis base. Let's check water as well. Water has 2 lone pairs. Am I right? This is water. That water is also a Lewis base. So compound with lone pairs are Lewis base. So and because ether has lone pair, so therefore this make ether a Lewis base, because ether can donate its electrons. So it can donate its electron to form coordinate covalent bond. So it can donate electron to form a coordinate covalent bond. Covalent, sorry. So by itself acting as a ligand, so can form a bond with that, and this can also happen to form an adduct. Some ether can form adduct. So when you say adduct is a compound form or the bond between Lewis acid and Lewis base. You get that? So for example now, this guy coming. This is ammonia, right? So this lone pair. So when it attached to a Lewis acid, so this is a boron fluoride. So this compound is said to be an adduct. So since ether also has lone pair, so ether can also some ether compounds, they are adducts, so they can act as adduct to a Lewis acid. So they can adduct a Lewis acid. So now this about the chemistry of ether. So and another thing that I also say about this chemistry of ether, the some interesting things about ether is that ether is used as organic solvent. So it can dissolve both polar and non-polar. Ether is not very polar, and as well it is not non-polar. So ether is between polar and non-polar. Ether is non-polar, and also you can also say it is also polar in some extent, because what makes ether polar is the presence of the double bond of oxygens. Let's check this now. So I've seen here. So this make ether polar because there is dipole moment. So there's dipole moment in ether. So that's why ether is polar, because of the oxygen carbon bond, so which make ether polar. And as well, ether is also non-polar in some extent, because there is there is so much of alkyl group. You get that? So in just one oxygens, there are a lot of carbons, so attached to the oxygens, you know. So that's why. So ether can act as both polar and non-polar, and as well, so it can dissolve both polar compounds and non-polar compound to some extent. That's why that ether is a very good organic solvent for organic compounds. Okay, so that's the thing about the chemistry of ether. So the next thing I'll talk about is reactions of ether. So about reactions of ether. So the first reaction that we talk about is coming. Now, the first reaction I'll talk about is what we call acid catalyzed cleavage of ether. Acid catalyzed cleavage of ether. So these reactions, we call it acid catalyzed cleavage. The cleavage of ether by acid, by strong acid. Okay, so in these reactions, we said ether are unreactive, but under vigorous conditions. So like when you have a strong acid, a very concentrated strong acid at high temperature, so ether undergo cleavage. So this compound, this acids can cleave ether into two compounds. And let's take for instance now, let's say we have this compound, this dimethyl ether, right? Okay, so reacting with a very strong acid like hydrogen iodide. So strong acid, we mean in this case, we mean hydrogen halide. So hydrogen halide can be hydrogen iodide, hydrogen bromide, or hydrogen halide. So it can be hydrogen iodide, or hydrogen bromide, or hydrogen chloride. But the most suitable, or the one that is the most reactive of all this acid, you get, the most reactive of all this acid is the hydrogen iodide, because the reactivity decreases as come down from this from the way I write it here. So iodide is most suitable because it is very very fast, because iodine can make iodide can make a good nucleophile. So that's why the reaction with hydrogen iodide with ether is the fastest compared to hydrogen bromide and hydrogen chloride. Okay, so the thing is this: what happens is that this acid will cleave this ether into two, just this way, very simple, this way. And from the acid we can see that we have hydrogen attached to iodine, right? So then the hydrogen will always protonate the oxygen, and the halogens will come to the carbon here, just like that. So therefore we have this compound. We have Ca3i, then we have Ca3, OH. So this is methyl iodide. And this is methanol. So therefore, a strong acid can cleave ether into two compounds, and haloalkanes can, or alkylate, haloalkane or alkylate join with what, and alcohol. So a strong acid can cleave ether to these two compounds into an alcohol and haloalkanes. Please note this aspect of ether very well, because questions came out from it very well in last semester. Last session. Okay, so the next thing is this. Let's say we now use please, this reaction take place under reflux. When I mean reflux is that we heat it slightly just to speed up the reaction, or to initiate the reaction by taking from to initiate the reactions to take place, you get, or to speed up the reactions, just heat it a bit, so without much heat. Okay, so let's say we now use excess acid, sorry. Let's say we use excess acid. In this case now we use excess of this guy. So we use excess of the acid, so we have a different situation. So we use excess acid, like the excess hydrogen iodide. So we have a different case, because after formation of the methyl iodide in this case and the methanol, so the methanol will be converted to, so because we have excess hydrogen iodide, so it will convert, it will still react with the ethanol and convert the ethanol to methyl iodide and water. So therefore, if we use excess iodide, excess hydrogen iodide, so we are going to have the two products to be what? To be haloalkanes. Please note it. So because we are going to form, though we are going to form ether first, but that forms, we are going to form alcohol first, but that alcohol that forms we later convert to ether. So we are using excess acid. So after the formation of the alcohol, so the alcohol will still react with the excess acid to form what? To form the hydrogen iodide. To form haloalkanes or alkylate back. Okay, so this is just the rough work for these reactions, but let's talk about the mechanism of these reactions, because this reaction is an SN reaction, nucleophilic substitution reaction. So it is not as simple as we talk about it here. So let's talk about the real mechanisms of the reactions, and there are some situations whereby we have to choose our products wisely. So let's talk about them. Now, let's check this compound. Okay. Let me just draw the structure from now. Let's check this compound now. This is methoxyethane. So let's say this compound is reacting. They gave us this compound like this. They now said This reaction with strong acid reflux. So what is the product? Which product are we going to form? So to deal with this reaction very well, so this is what I'm going to do. So you can't just cleave anyhow. Yet, so you can't just cleave anyhow. There are mechanisms that take place during the cleavage. So now let's look at them. So the first thing is that the strong acid. You have to know something here. The strong acid, the bond between the strong acid is this, and since it's a covalent bond, so, and the iodine being more electronegative than the hydrogen, so it will withdraw the electron to itself, and this will lead to partial positive, partial negative, and leaving partial positive on the hydrogens. So that's the first thing. This is one of simplest thing you have to know. Okay, so these steps now, the first thing that take place is this. The first step that take place is this. That step is what? Protonation of the ether. Protonation. You know, I said ether is non-reactive, so you have to protonate ether to make it active. So, and from by protonations, so this is what we mean. The hydrogen is positive charge. Am I right in this case? So as you see that positive charge means that it's an electrify. Am I right? Electrify. And electrify, the one of their function is that they attack nucleophile. So if you come to ether, so oxygen carry lone pairs of electrons. Therefore, oxygen is what? Oxygen is a nucleophile. So what happens is that the hydrogens will come and attack the oxygen. So once it attacks the oxygen, so the oxygen will bond with the hydrogens and carry positive charge directly. So therefore we have this compound. So we have now positive charge. Okay, so then the iodine is still waiting. You get? So, but the major reason why we protonate is that we want to make the alkoxy. We want to make the oxygens a very good a good living group. So that's why we protonate it, so that it will make it a good living group. Okay, so since we are protonated now, the next step is the what you call nucleophilic substitutions. So nucleophilic substitutions, that's the next step. So the SN, that's the next step now. Now the iodine now I want to combine. That's the next step. The iodine that carries negative charge now want to combine with the protonated ether. So where do you think the hydrogen will go? Because at the iodine will go. Because check these two carbons that are attached to the oxygens. You check, okay, which carbons do you think the iodine will attach to? So to decide about that, so you check which of these carbons, the two carbons are, this carbon is a primary carbon, and this here is a what? Is a methyl carbon. Am I right? This is a primary carbon. Primary carbon, and this is a methyl carbon. Okay, so the very thing is this: the iodine will go to a less substituted carbon. Look at that, a less substituted carbons. And in this case now, the iodine, instead of coming to primary carbons, so it's better to come to what? To a methyl carbon from the back. So to attach methyl carbon from the back, and as it's attached to methyl carbon from the back, so the oxygen together with the remaining compounds, they will leave. So they will leave. So as they leave, so what happens? So we have this compound, we have, so the iodine is here attached from the back, then the carbon has pursued away the other compounds, so then we have so we have so we have CH3 CH2 OH, because this is CH3 CH2 OH. So maybe I just draw it structurally so that you can understand better. Then so, and this is what this just like writing C3 C2 OH. So this methyl iodide, and this ethanol. So this reaction is said to be SN2 reactions. SN2 reactions. The reason why it's SN2 reaction is this: because the two carbons that are attached to the oxygens, two of them, they are not tertiary carbons. So it's only when you have tertiary carbons, that's when you can have SN1 reactions. So once you have primary or primary or methyl carbons attached to the oxygens, so you cannot have SN1 reaction in that case. You get that? So, and since we don't have the tertiary carbons, it means that the iodine or the iodide will have to attach to the methyl carbons or the less substituted carbons. Then the dark carbons will now lose the leaving group. So the two of them are working. The iodine is working, then the compound or the carbon that is attached by the iodine is also working. So we have SN2. So the reaction depends on the concentration of the two reactants, the iodine and the compound that has been attached. Okay, so the next thing is the SN1 reactions. And to explain SN1 reactions, so let's check this example. For SN1 reactions, let's check this example. So let me explain SN1. So this one, let's say we have a tertiary carbon, this is also an ethyl compound, then reflux. Okay, so the first thing that takes place, you know that now. So from this we can deduce that so the hydrogen is positive charge and the iodine is negative charge. So what happens first is this protonation, right? So we have protonations. So for protonations, So the for protonations, the hydrogen will protonate the oxygen. So then we have a protonated ether. So we have alright. So we have hydrogens, positive charge, then we have Ca3. So now, since we have gotten protonated ether now, so this reaction is SMR reaction because of what? We check these two carbons that are attached to the oxygens. One of them is tertiary carbon, and this is what? This is tertiary carbons. Am I right? So since we have a tertiary carbon and this is a methyl carbon, so once you have a tertiary carbon, you should know that that reaction should be SN1 reactions, because this reaction, it is lesser, or it requires less energy to lose, for this carbon to lose this leaving group, to lose it, rather than the iodine to attach to the less substituted carbon. Let me say it again. This reaction, it is SMR reaction because we have tertiary carbons. So, and for tertiary carbons, so it is easier for tertiary carbons to lose this alkoxy and the methanol, the oxygen part, to lose it, to lose the fragment, rather than the hydroxide and the iodine to attach to the less substituted carbons like we did in SN2 reactions. So that's why these reactions goes without the interference of iodine. So this reaction, so the first thing that since it's an SMR reaction, so the next thing that happens is that without iodine being attached to anything, so the reaction takes place itself, and we have these things. So we have, then this carbon will lose the hydroxide, the alkoxide itself, the methanol itself. So since it's a tertiary carbon, so we have CH3OH. Then there's iodine still waiting. Am I right? So iodine with negative charge is still waiting. So the iodine with negative charge will now come and join. So then we have Ca3, iodine. So simple. So we have formed two products. So we form methanol. So we have formed methanol, and we have formed tertiary acrylide. So these are the two compounds we have formed now. So we have formed methanol, so we have formed 2-methyl 2-iodo 2-methyl propane. Sorry, 2-iodo 2-methyl propane. 2-iodo 2-methyl propane. So this is also an acrylide, and this compound, to name this compound, this also name it compound. So this is locus carbon, and this attachment. So this iodine, this methyl. So therefore carbon 2. Therefore we have 2-methyl. Between M and I, which one comes first? I now. So now I. So we have 2-iodo 2-methyl propane. And this is what? This is methanol. So this is how to deal with SN1 reactions. So just check the two carbons that are involved with oxygens. Is there a tertiary carbon there? So if it is a tertiary carbons, therefore the reaction will take place in SN1 reaction. So and the compounds will lose the oxygen itself together with other compound attached to oxygens. Then the iodine will join. But if it's SN2 reaction, it means that the iodine will come and join with the less substituted carbons. Then that carbon will now lose the oxygen part, the other carbons that remain. So that's it. Now, let us say we use excess acid. So if we use excess acid, this is what is going to happen. This is what we're going to have. Let's say we use excess acid. So let me clean this guy. So we use excess acid. So the methanol formed. So the methanol forms, we still go and react with the the methanol. Let me draw it as a chemistry student. So the methanol formed. This is methanol. So the methanol formed, we come and react. We react more with the strong acid. So and what do you think will happen? Same thing will happen. So we have protonations. So the hydrogen will protonate the oxygens. Then we have these compounds plus then and the next thing is this. So since the we have only primary carbon here, so the iodine, so these are SN1 reactions, right? And these SN2 reactions, am I right? So I think you're able to differentiate between SN1 and SN2 now. So the come and attach from the back because the carbon is primary carbon, so methyl carbon rather. So and once that happens, so this guy will leave. So and we have Ca3 sorry, we have this, then we have H2, you get. So this red one will form H2. So it means that whenever we use excess acid, so we are going to have two products. We are going to have only haloalkane formed because the methanol formed on the alcohol that formed will later be converted to haloalkanes. You get, depends on the acid that we use. So later converted to haloalkanes by the strong acid if it's excess. Okay, so and this version depends on the acid because we use hydrogen iodide, so the reaction will go faster than using hydrogen bromide compared to using of hydrogen chloride. Because the reason is that hydrogen iodide produce iodide, which is a very good nucleophile. Compared to bromide and chloride, do you get? So that's why that these reactions is goes faster with strong acid of hydrogen iodide. Okay. If you have aromatic compounds, let's say we have aromatic ether. Let's say we have aromatic ether like this now. So let's say we have aromatic ether. So reacting with strong acid reflux. So what I'm going to have is this. The first thing is that the acid, the acid will protonate the hydrogens. So after protonating the hydrogens, what do you think will happen next? So we have protonated ether, and from protonated ether, we have protonated ether. The positive charge is that it is showing that the oxygen has used one of the lone pair to form bond. So then we check these two carbons. So there's one carbon here, there's another carbon here. So two of them, they are not tertiary carbons. So what will happen is the iodine will come to a less saturated carbons. So the iodine will come to this carbon from the back, and we're going to have this compound CA3I. Then we have phenol. Because as the iodine joins with the methyl, so what happens to the other part? So this guy here, so they will leave as what? As phenol. So please note, even if you use excess acid, so the phenol will not convert to halide. Do you get that? So the phenol will not be converted to acrylide, even if you use a very strong acid. So excess acid. So the phenol will not be converted to acrylide. So here we have methyl iodide and phenol. So this is for aromatic ether. Alright, now similarly we can also have reactions, cleavage reactions with pentachloro I'm coming now. Okay, I want to clean this piece. Now we can also have similar reactions with PCl5. Okay, so yes, we can also have these similar reactions with PCl5. So, but this one can, though it can cause cleavage of ether, but it will not produce alcohol. Please note it can only produce acrylide or haloalkanes. Do you get? So let's say we have Ca3, Ca2Cl. Sorry. Now reacting with PCl5. So the function of this guy is that it will just cleave. Though it's a very long mechanism, but let me just cut it short. So it just cleave this guy into two. So after cleaving it to two, so to now donate each oxygen chlorine to each of them. So this one becomes Ca3, Ca2Cl, and this one becomes Ca3Cl. Then the oxygens, so out of 3 chlorines, which remains 2 chlorine. Out of 5 chlorines, remains 3 chlorines. So then the oxygens will come and do insertion. So therefore you have POCl3. So These are the products of chlorination of ethyl methyl ether with PCl5. So no alcohol will produce. So and note these products. I think they can ask this thing. So alright. The next thing I'll talk about is how can we prepare ether in the laboratory. So the synthesis of ether. So how can we synthesize ether? So one of the ways to synthesize ether is I will talk about 3 ways in which we can, or 3 reactions that can produce ether. So one of them is Williamson ether synthesis. So Williamson ether synthesis. Now, these reactions or this process synthesize. Okay. Now, with this Williamson ether synthesis, this method is suitable for both symmetrical and unsymmetrical ether, and it is in 2 steps. So the first step is that you react alcohol with a strong base. So let's say we have alcohol. Let's pick any alcohol. Let's pick ethanol. A very common alcohol. So this is ethanol. So this alcohol you react an alcohol with a very strong base like sodium hydride. You know, a very strong base, then reflux. Okay, so this what happens here is this: after reacting with, like dissolving or mixing ethanol and sodium iodide solutions together, so the process will happen and we have from sodium iodide. So sodium is positively charged and this guy is negatively charged. Yes, because hydrogen is more negative than sodium. So what happens is this. But before that, this nucleophile between the oxygens and hydrogens. So oxygen is more negative than hydrogen. Therefore, oxygen will withdraw the 2 electrons to itself. To get that. So and by doing that, so we have this Ca3. Oh, I think there's a mistake here. Ca2. Then we have alkoxide being formed. So then the hydrogen left as positive charge. Do you get? So then from here, so the hydrogens from this place, here we give sodium plus and iodine negative. So the hydrogen from here we meet with this one and they form hydrogen gas, so which can evaporate and leave the reactions. Then we have sodium ion or sodium ions left and the alkoxide. This guy is called alkoxide. So and in this case, since it's 2 carbons, we call it ethoxide. Ethoxide ion. So we call it ethoxide ion. So the sodium can combine with the ethoxide ion and form sodium ethoxide. You get that? So but let's say the reaction continues with ethoxide, so ethoxide ions. Then the next step, this is the first step of Williamson synthesis. The next step is that The first step produced alkoxide ion. Then the next step is that the alkoxide ion produced, in this case the ethoxide ion produced, the ethoxide ion produced will now react with acrylate. So let's say we have with methyl bromide. So this is the next step. So, and in this step, what happens? So this step is a nucleophilic substitution step, and in fact it is an SN2 step. How? Because let's see the structure of methyl bromide. Okay, and this is oh sorry. Alright, so what happened here is that the alkoxide is a nucleophile because it is carrying positive charge, I mean it's carrying negative charge, so it's a nucleophile. So it will and this carbon here is a methyl carbon. Am I right? So the nucleophile will attack from the back. So it will attack from the back, and this bromine will make a leaving group. So it will become a leaving group. So it will leave as bromide. Then we have this product. So we have this product, Ca3, Ca2, O, then sorry. Do you see? Then this bromine that left with negative charge will combine with the sodium from the first reaction. Do you see? So and combine with sodium from the first reaction, and they form sodium bromide. So then this reaction, this product is what? Is an ether, because if you take it very well, see that this is ethyl methyl ether. So this is it for Williams-C synthesis of ether. So once you have ether compounds, so you start with alcohol. So you have to be alcohol with a very strong base to produce alkoxide. So it depends on the number of carbons in alcohol, determine the number of alkoxide to produce. Then the alkoxide will react with an acrylate to produce the ether. And the reaction of acrylate with the alkoxide is an SN2 reaction, because the alkoxide will displace, we replace the, or we substitute the halogens that is in the acrylate. So, and let me tell you something. The choice of acrylate that we use, you must very, very clear about that, because the acrylate we use must be a primary or a methyl acrylate. If you use secondary or tertiary, so this is not suitable. So you can only use either of primary or methyl iodide. Even it is better to use a methyl iodide rather than using primary or secondary or tertiary, because this secondary or tertiary we form elimination reactions which is not suitable for the reaction we want to do. So you can either use primary or methyl acrylate. Do you get? So please note it. So you cannot use a secondary or tertiary acrylate in this case. Okay, so this is about Williams-C ether synthesis. So the next one we talk about is dehydration of alcohol. So this is another way to synthesize ether in the laboratory by dehydration of alcohol. And these ones, let's go some steps backward. Now, during dehydration of alcohol, to form alkane. Let's say we have propanol or propanol. Okay, this is propanol. Now, so this under reacting with conc HSO4 under about 180 degrees Celsius. So this reaction is the addition reactions. What happens is that these reagents will remove the oxygens, hydroxides and water, and hydrogen, that is water. So it dehydrates the alcohol to give alkane. And this since you remove hydrogen from carbon 1, carbon 2, since you remove hydrogen and hydroxide from carbon 1, from this carbon and this carbon, so there will be a double bond formed between the two carbons. So, and these so, and this is so this is an alkene. So, and this is 18, to be precise, 18. So therefore, this reaction is a complete dehydration reactions. So, but to produce ether, so we don't need complete dehydration. So we need incomplete dehydration. And in this case, we have to put ethanol, the alcohol, to be in excess. So since we have excess alcohol, so like 2 molecules of alcohol, then limited reagents. So for example, now let's say we have ethanol, 2 molecules of ethanol, and so reacting with H2SO4 under like 140 degrees Celsius, not up to 180. You see. So in this reaction now, this will lead to incomplete dehydration of alcohol, and we have this. So the water molecule will be removed from 2 molecules of alcohol. One water molecule will be removed from 2 molecules of alcohol, and this will lead to the formation of ether. So this is ether. Alright, so these dehydration reactions is very good in producing symmetrical ether. So it's not suitable for producing unsymmetrical ether. So only symmetrical ether is very suitable by these reactions. So the addition of alcohol. Then another and these reactions this reaction is also an enzyme reaction. It's also an enzyme reaction. So even it is so if the alcohol is an enzyme reactions, but to determine if it's SN1 or SN2, so it depends on the alcohol. So if the alcohol that you are using is a secondary or tertiary alcohol, so the reaction is an SN1 reaction. But if it is a primary or a methyl alcohol. So the reaction is what? Is a SN2 reactions. Okay, so lastly, so the reactions of haloalkanes with dry silver 1 oxide. So this is another way to produce. Let me use this. So this reaction is very important because haloalkanes reacting with silver 1 oxide can also produce ether. So in this case now you need 2 molecules of acrylide. So then silver 1 oxide. So then you need to reflux or you warm. So what happens is this: the 2 molecules of the acrylide. So the dry silver 1 oxide will remove the 2 halides and insert oxygen in place. So the actions now give something like ROR. So then to form So this is the reactions of haloalkane with dry silver oxide. So it will just remove the 2 halide hydrogens and put oxygen there. For example, now let's say we have methyl bromide, 2 molecules of methyl bromide, 2 molecules of it. So reacting with silver 1 oxide. So it means we're going to have, it means that this silver 1 oxide will remove the bromine and put the oxygen there. So, and as a result, I will have Ca3O, Ca3. So this is methyl dimethyl ether. So this is how to produce ether in laboratory. So these are the reactions to produce ether. So as a summary, we are going through Wilhelm C interactances. We have gone through the addition of alcohols and reaction of acrylides with silver 1 oxide. Okay, so take care of yourself and watch the video. If it's very complex to understand, go over it again. It's very simple. And if you have any questions, try to enter my DM. I will gladly attend to you. Take care of yourself.